Welcome to another episode. Before we begin, I'd love to know where you're listening from and what time it is there right now. Share it in the comments below. It's always fascinating to see where curiosity connects us across time zones and stars. And if you enjoy drifting through these quiet explorations, consider subscribing. It helps the channel grow and keeps this little corner of the universe glowing. Now, let's begin. Imagine the final breath of a giant star. For millions of years, it burned bright, fusing hydrogen into helium, helium into carbon, carbon into heavier and heavier elements, each layer stacked like the rings of an ancient tree. Then, suddenly, the balance breaks. Gravity, that silent sculptor of the cosmos, wins the battle. The core collapses inward, faster than thought, faster than light can cross the dying star's width. Atoms themselves crumble, electrons are crushed into protons, forming neutrons. And in the violence of that collapse, an explosion so vast it can outshine an entire galaxy for days, a new kind of object is born, a neutron star. A neutron star is the corpse of a massive sun compressed into a sphere just about 20 kilometers across, roughly 12 miles, but heavier than our own sun. To put that in perspective, a teaspoon of neutron star matter would weigh as much as Mount Everest. It's the densest form of matter that can exist without collapsing into a black hole. If you could somehow stand on its surface, not that you could survive, gravity would pull you down with 200 billion times the force you feel on Earth. These remnants are already among the strangest things nature allows, but among them, a few are stranger still. A rare breed of neutron stars are born not just dense, but magnetic, with magnetic fields so powerful they defy imagination, reason, and the limits of physics itself. These are magnetars, the most magnetic objects known to exist. The term magnetar was first proposed in 1992 by two astrophysicists, Robert Duncan and Christopher Thompson, at the University of Texas at Austin. At the time, scientists were puzzled by mysterious bursts of high-energy radiation coming from deep space, flashes of soft gamma rays that didn't quite fit the behavior of known neutron stars. Duncan and Thompson suggested something radical, that these bursts were caused by neutron stars whose magnetic fields had reached such an intensity that even the structure of atoms would be distorted by them. They called these monsters magnetars. To understand how extreme that really is, let's start close to home. The strongest magnetic field you can generate on Earth in a laboratory is around 100 Teslas. That's about 2 million times stronger than a typical refrigerator magnet. It's enough to lift a car if it could be sustained, but a magnetar's magnetic field can reach 10 to the 11th power Teslas. That's 1 followed by 11 zeros. That's a billion times stronger than the magnet on your fridge, and 1 trillion times stronger than Earth's own magnetic field. If one of these cosmic magnets somehow appeared halfway to the moon, about 190,000 kilometers away, it could erase every credit card on Earth. If it came within 1,000 kilometers, about 620 miles, the magnetic forces would literally distort the atoms in your body, pulling them into elongated shapes. The electrons in your brain would follow magnetic field lines instead of your neurons. Reality itself would feel rewritten. Yet from a distance, a magnetar looks peaceful. A small, spinning sphere of light about the size of a city, quietly rotating once every few seconds. But inside, magnetic forces twist and tear the crust, releasing bursts of X-rays and gamma radiation powerful enough to shake detectors across the solar system. In some cases, these explosions release as much energy in a single second as the sun emits in 100,000 years. They are paradoxes of creation, serenity and catastrophe held together in perfect balance. And the mystery deepens when we ask how they came to be. Most neutron stars are born spinning rapidly, dozens or even hundreds of times per second. That rotation combined with the movement of charged particles in their dense interior can create strong magnetic fields, a kind of dynamo effect, similar in principle to how Earth's magnetic field is generated, though on an incomprehensibly larger scale. But magnetars seem to take that process to the extreme. They may form when a collapsing star spins particularly fast, perhaps once every millisecond, and the resulting turbulence and convection inside the newborn neutron star amplifies the magnetic field to colossal strength. It's a cosmic version of winding a dynamo until it nearly breaks. The details are still uncertain. We can't watch a magnetar being born directly. The event would be hidden deep within the blinding chaos of a supernova. But computer simulations suggest that if conditions are right, if the rotation is fast enough and the convection vigorous enough, magnetic fields can grow explosively in just a few seconds after the core collapses. Then, as the star cools, that magnetic energy becomes frozen into its crust, a permanent scar of the violence that made it. When Robert Duncan and Christopher Thompson proposed this in 1992, it was considered speculative, even outlandish. Yet within a decade, observations began to confirm their idea. Astronomers studying peculiar X-ray and gamma-ray bursts realized they all seemed to come from neutron stars, with unusually slow rotation and extreme magnetic braking, exactly what magnetar theory predicted. The first confirmed magnetar, known as SGR 0526-66, had actually been detected years earlier in 1979, during a mysterious gamma-ray flare from the Large Magellanic Cloud. But it wasn't until the theory existed that the puzzle pieces fit together. What Duncan and Thompson gave us wasn't just a new kind of star, it was a glimpse of the universe operating at its most intense limits. These objects push the boundary between what matter can endure and what physics can describe. At their surface, the magnetic field is so strong that empty space itself behaves differently. Quantum electrodynamics predicts that in fields stronger than about 10 to the power of 9 teslas, the vacuum becomes polarized, meaning that even the emptiness between particles can bend and twist light. In a sense, magnetars don't just warp space, they warp the laws that describe it, and yet they remain almost invisible. You could place a magnetar at the distance of the nearest star, Proxima Centauri, about 4.24 light-years away, and it would be too small to see, even with our best telescopes. Only its bursts betray its presence. They flicker across space like cosmic heartbeats, quick pulses of energy, each one a message from a star that should no longer exist. There's a quiet poetry in that, a dead star, silent and collapsed, still speaking to us through the language of magnetism and light. It's as if the universe keeps whispering that even in death there's something left to say. And what it's saying is extraordinary, that there are places out there where the rules of our world simply break. Where magnetism, that invisible force that sticks notes to your fridge and guides compasses north, becomes a cosmic weapon, strong enough to tear matter apart. It's easy to forget that the same fundamental force that shapes a magnetar's violence also shapes the gentle auroras above our poles and the spinning cores of galaxies. Magnetism, in all its scales, connects us to the very architecture of the cosmos. So tonight, as you listen to the slow crackle of the fire and let your thoughts drift beyond Earth's calm magnetic cocoon, imagine a place where that calm becomes chaos, where every atom is strained by forces that should not exist, and yet somehow do. A neutron star, small, dense, spinning in the dark, holding inside it one of nature's deepest enigmas, the power of impossible magnetism. And in the next breath of our journey, we'll step closer to the event that births such objects, the collapse of a star so massive, so unstoppable, that even death becomes a form of creation. The life of a massive star is a story written in fire. For millions of years, it burns with relentless energy, fusing lighter elements into heavier ones in a delicate balance between gravity and pressure. Inside its core, atomic nuclei collide with such force that hydrogen becomes helium, helium becomes carbon, carbon becomes oxygen, and onward, each new fusion stage feeding the star's radiance. But this balance has an expiration date. A star between 8 and 30 times the mass of our Sun spends most of its life fighting against its own weight. Gravity wants to pull everything inward. Fusion pushes outward. For most of its life, this tug-of-war ends in a stalemate, producing light, warmth, and stability. But when the core begins to forge iron, an element that doesn't yield energy when fused, the equilibrium breaks. Iron is the universe's dead end for fusion. It takes more energy to fuse than it gives back, and so, deep inside the heart of a massive star, the furnace starts to fail. When that happens, the star's entire life, millions of years of burning, ends in a moment of catastrophic collapse. In less than a single second, the immense weight of the outer layers falls inward, crushing the core with such violence that it becomes one of the densest objects imaginable. Let's pause for scale. The core of a star might contain a mass greater than the Sun, packed into a region roughly the size of Earth. As it collapses, electrons are forced into protons, merging to form neutrons, a process called electron capture. In this instant, atomic structure itself ceases to exist. The boundaries that define atoms, those vast spaces between nucleus and electron, vanish. What remains is a fluid of neutrons, crushed together so tightly that a single teaspoon of this matter would weigh about 1 billion tons. This process is halted only by an extraordinary form of resistance, neutron degeneracy pressure. It's a quantum mechanical effect, a rule born from the Pauli exclusion principle, which states that two fermions, like neutrons, cannot occupy the same quantum state simultaneously. In essence, even the subatomic particles protest against being packed too tightly together. This invisible rule of quantum nature becomes the final wall against gravity's absolute collapse. When the collapsing core hits this barrier, it rebounds, sending a shockwave hurtling outward through the infalling material. That rebound, amplified by neutrino interactions and other chaotic forces, triggers one of the most spectacular events in the cosmos, a supernova explosion. In the blink of an eye, the outer layers of the star are blasted into space at 1/10 the speed of light, scattering carbon, oxygen, and iron, the ingredients for planets and life, across the galaxy. For a brief time, that dying star can outshine every other star in its host galaxy combined. The luminous remains of such an explosion might expand for thousands of years, forming beautiful nebulae like the Crab Nebula, still glowing from the shock of its birth 1,000 years after its light first reached Earth. But at the heart of the wreckage, hidden beneath the swirling debris, lies something new, the neutron star. It's difficult to grasp just how extreme this object is. Imagine compressing the mass of the Sun, 2 non-Illian kilograms, that's a 2 followed by 30 zeros, into a sphere only about 20 kilometers wide, or roughly 12 miles. That's the distance of a morning commute across a city, yet it holds more mass than 330,000 Earths. The surface gravity of such an object is about 200 billion times stronger than Earth's. Drop a pebble from 1 meter above the surface, and it would hit the ground at 1/3 the speed of light. Inside this neutron star, matter is in an exotic state beyond anything we can recreate. The surface crust may consist of iron nuclei embedded in a sea of electrons, beneath which lies a strange landscape of nuclear pasta. Layers and filaments of neutrons arranged in shapes whimsically named spaghetti, lasagna, and gnocchi by physicists. Further in, the core might contain superfluid neutrons, superconducting protons, or even free quarks, the building blocks of protons and neutrons themselves. It's not a star as we know it. It's a fragment of the early universe, a reminder of how extreme matter can become when gravity takes command. Most neutron stars we detect are pulsars, rapidly rotating beacons that emit narrow beams of radio waves, sweeping across space like cosmic lighthouses. The first was discovered in 1967 by Jocelyn Bell Burnell and Anthony Hewish when they detected regular pulses of radio energy coming from an unseen source in the sky. At first, they half-jokingly labelled it LGM1 for Little Green Men, because no natural process was known to produce such perfectly timed signals. It turned out to be a rotating neutron star, spinning dozens or even hundreds of times per second, emitting a beam from its magnetic poles that happens to cross Earth with each rotation. Since then, we've catalogued thousands of them, each ticking with the precision of an atomic clock. But among these neutron stars, a tiny fraction behave differently. They spin more slowly, their pulses are irregular, and sometimes, unpredictably, they erupt with bursts of high-energy X-rays and gamma rays. These are the magnetars, and they are born in the most violent conditions imaginable. To understand how a magnetar is made, we need to look back to those first few seconds after a massive star's core collapses. The newborn neutron star is unimaginably hot, about 1 trillion kelvins, and it spins rapidly, possibly hundreds of times per second. That rapid rotation, combined with turbulent convection inside the fluid interior, creates a dynamo effect, a process where moving, electrically charged matter generates a magnetic field. This is the same fundamental process that creates Earth's magnetic field, but the scale is incomparable. In a proto-neutron star, convection cells swirl and churn in just a few milliseconds, and rotation happens so fast that the entire star completes dozens of turns before it has even cooled slightly. The result is an amplification of the magnetic field far beyond anything ordinary neutron stars achieve. The field can grow explosively, reaching 10 to the 11th power teslas in less than 10 seconds. For comparison, the strongest magnetic fields we can produce in laboratories on Earth barely reach 100 teslas before the equipment vaporizes. A magnetar is literally 100 billion times stronger. This magnetic energy doesn't just sit quietly, it exerts pressure, enough to twist and crack the neutron star's crust, releasing bursts of X-rays. It slows the rotation dramatically, as magnetic drag drains the star's rotational energy. Where a typical pulsar might spin hundreds of times per second, a magnetar slows down quickly to a period of 2 to 12 seconds. In just a few thousand years, it can lose most of its rotational energy, leaving behind a slower, quieter, but still violently magnetic remnant. The difference between a pulsar and a magnetar is, at its core, one of scale. Both are neutron stars, born in supernova explosions. Both have intense gravity and spin with the precision of a cosmic engine. But where a pulsar's magnetic field might reach around 100 million teslas, a magnetar's can climb to nearly 100 billion teslas. That may not sound like a huge difference, but magnetism increases non-linearly. It changes the behavior of matter itself. In a magnetar, the field is so intense that it dominates every other force except gravity. In such an environment, atoms are no longer spherical. Their electrons are forced into tight, elongated orbits along magnetic field lines. Even the vacuum around the magnetar is altered. It becomes birefringent, meaning light travelling through it splits into two polarizations, just as light splits through a crystal on Earth. This is not a theoretical curiosity. In 2016, astronomers using the European Southern Observatory's Very Large Telescope detected this exact effect from a neutron star known as RxJ 1856.5-3754, likely a magnetar or near magnetar. It was the first direct evidence that the void around these stars behaves like a prism, bending light in ways quantum physics had predicted but never before seen. To put magnetar strength into human terms, imagine you could somehow bring one into our solar system. Place it halfway between Earth and the Moon, and the magnetic field would be strong enough to scramble every digital device, erase every hard drive, and tug gently on the metallic objects in your home. At a distance of just a few hundred kilometers, it would begin to pull your atoms apart. The iron in your blood would align to the field, and the molecules in your body would no longer hold together the way chemistry intends. Fortunately, the nearest known magnetar is around 9,000 light-years away, comfortably distant, though still visible to our telescopes as a flickering X-ray point of light. Yet despite their incredible power, magnetars are also ephemeral. Their magnetic fields decay over time, typically in about 10,000 years. That might sound long to us, but in cosmic terms it's a brief spark, a blink compared to the million-year lives of ordinary neutron stars. As the field decays, the star's violent outbursts fade, and it gradually settles into a quieter existence. indistinguishable from a normal pulsar. Magnetars are the short-lived fireworks of the neutron star family, bright, erratic, and intense. What's still not entirely understood is why some neutron stars are born as magnetars and others as ordinary pulsars. It may depend on the mass of the progenitor star or on the speed of rotation during collapse. A star spinning faster at the moment of collapse can sustain stronger dynamos. There's also evidence that metallicity, the amount of heavier elements in the star, might play a role since it influences how the star loses angular momentum before death. Another hypothesis suggests that the presence of strong convection in the proto-neutron star enhances magnetic amplification through what's called an alpha-omega dynamo, a process also thought to power the sun's magnetic cycles, though at far lower intensity. Whatever the cause, the outcome is one of nature's rarest tricks. A sphere no larger than a city, but with a magnetic field capable of distorting space-time and changing the properties of light itself. When we observe a magnetar's flare, a sudden burst of energy in the X-ray or gamma-ray range, we're witnessing the magnetic crust snapping under the strain of its own internal forces. The star literally suffers from cosmic earthquakes, or starquakes, each releasing more energy than 1 billion nuclear bombs. The ripples from those quakes race outward at near-light speed through magnetic fields that can twist and reconnect, launching streams of radiation across space. It's astonishing to think that this begins as a simple act of gravity. A star running out of fuel, its fusion fire extinguished, collapsing under its own weight. From that death, in less than a heartbeat, comes one of the most exotic creations in the universe. Magnetars remind us that endings in the cosmos are never really endings. A dying star is not just an explosion, it's a transformation. The same force that tears a world apart can forge something entirely new, denser, stronger, stranger. It's a kind of cosmic recycling, and magnetars are the brief, dazzling proof that even destruction can give birth to wonder. As the supernova's fading glow drifts across space, the newborn magnetar spins in the dark, invisible to the human eye, yet powerful enough to sculpt its environment for centuries to come. In that faint remnant lies the seed of magnetic storms so immense that thousands of years later their echoes still reach us as bursts of radiation from across the Milky Way. And as we turn our gaze toward those distant bursts, we begin to uncover the restless nature of these magnetic titans, stars whose inner power cannot be contained for long. Soon we'll watch as that buried magnetism starts to rupture the surface itself, shaking the universe with flashes of light unlike anything else in nature. At first glance, magnetism seems ordinary, familiar, almost domestic. A magnet sticks to your fridge. A compass needle trembles north. We see it as something simple, an invisible but obedient force. Yet, at its heart, magnetism is one of the strangest consequences of physics, a bridge between electricity, motion, and the very structure of matter. To understand the power of a magnetar, we have to strip this everyday force back to its foundations, to the level of the particles that make up everything we know. Magnetic fields are not substances. They are relationships, patterns in space created by motion. When an electric charge moves, it creates a magnetic field around it. You can picture it as invisible loops wrapping around the path of that motion, curling through space like the eddies that swirl behind a stone dropped into water. The faster or more concentrated the charge, the stronger the field. Even the spin of a single electron generates a tiny magnetic field, a quantum-scale whirlpool of energy. Inside every atom, billions of these tiny fields overlap and combine. Usually they cancel each other out, which is why most materials are not magnetic at all. But when enough of them align, when their spins fall into step, the magnetic field becomes macroscopic, stretching beyond the atom to shape the world around it. Now, imagine scaling that up to the size of a star. Before its death, a massive star is a churning ocean of plasma, a fluid of free electrons and nuclei moving at incredible speeds. These charges, swirling in vast convective currents, naturally generate magnetic fields. In most stars, those fields are moderate. The Sun's surface magnetic field, for example, averages around 0.0001 Tesla, roughly the strength of a common refrigerator magnet. Even in its strongest sunspots, it rarely exceeds about 0.3 Tesla. That's enough to shape flares and coronal ejections, but nothing compared to what's waiting in the heart of a collapsing star. When the core of that star collapses into a neutron star, something extraordinary happens: magnetic compression. Because magnetic flux is conserved, meaning the total number of magnetic field lines passing through a surface remains constant when that surface shrinks. The field strength rises dramatically as the star's radius contracts. Imagine compressing the Sun down to the size of a neutron star just 10 kilometers, 6 miles across. That's a reduction in size by a factor of about 70,000. Because the field scales roughly as the inverse square of the radius, the magnetic field would intensify by a factor of 70,000 squared, nearly 5 trillion times stronger. That alone would create a field of about 10 to the 8th power Teslas, already enough to strip electrons from atoms. But that's only the beginning. In certain cases, something even more dramatic unfolds: a dynamo mechanism deep inside the newborn neutron star. When the core first collapses, it's not a solid sphere but a violently convecting superheated fluid. Temperatures exceed 1 trillion degrees Kelvin, and the newborn star may spin hundreds of times per second. That combination, intense rotation and turbulent convection, is exactly what's needed for a magnetic dynamo to form. On Earth, our planet's magnetic field arises from a similar process: molten iron circulating in the outer core, moving through the planet's rotation to generate electric currents. But inside a proto-neutron star, the same physics is cranked up to cosmic extremes. Instead of molten metal, it's a sea of charged particles, mostly neutrons, protons and electrons, moving at relativistic speeds. And instead of one rotation every 24 hours, the neutron star spins 100 times per second or more. These conditions can stretch and twist the magnetic field lines like taffy, winding them tighter with each rotation. In just a few milliseconds after collapse, the field can amplify by another factor of 1,000 or more. The result is a magnetic field that reaches 10 to the 11th power Teslas. To put that into perspective, that's 100 trillion times stronger than the magnetic field of a typical medical MRI machine, and billions of times greater than anything we can generate on Earth without destroying the apparatus instantly. At this point, the magnetic field is so intense that it dominates the physics of the star. It exerts pressure, magnetic pressure, that can compete with the pressure of matter itself. It can twist the star's crust, slow its rotation, and even alter its shape slightly, making it more like an oblate spheroid than a perfect sphere. In some cases, it can also create instabilities, as the magnetic field rearranges itself to find a more stable configuration. When those rearrangements happen suddenly, the star releases immense bursts of energy, starquakes, the Magnetars version of an earthquake. These starquakes occur because the crust of a neutron star, though solid, is under enormous strain. The magnetic field, locked into the crust, is constantly shifting and decaying. As it tries to realign, it can fracture the rigid outer layers, releasing stored magnetic energy as a burst of X-rays or gamma rays. Each event can release 10 to the power of 34 joules of energy, roughly the total output of the Sun over a week, unleashed in less than a second. Astronomers detect these events as soft gamma repeaters, short, intense flashes of high-energy radiation that appear and disappear unpredictably. The name soft is misleading. Even the mildest magnetar flare is catastrophic on human scales. A particularly powerful one, such as the 2004 giant flare from Magnetar SGR 1806-20, released more energy in a fraction of a second than the Sun emits in 100,000 years. If such an event occurred within 10 light-years of Earth, it would likely strip away our ozone layer. The source of this unimaginable energy is the magnetic field itself, a reservoir storing and releasing energy in a way that's almost alive. We can calculate the magnetic energy density using a simple formula from classical electromagnetism. Energy per cubic meter is proportional to the square of the magnetic field strength. At 10 to the 11th teslas, that's about 4 times 10 to the 34th joules packed into the volume of the star. It's hard to visualize such numbers, but imagine every power plant on Earth running at full capacity for 1 billion years and still falling short. But what makes magnetars especially fascinating is that these aren't just big magnets. Their fields are so strong that they change the very rules of matter. In normal conditions, magnetic fields affect moving charges. They steer electrons, align spins, and create magnetic domains. But at field strengths above about 10 to the 9th power teslas, even the vacuum of space becomes affected. According to quantum electrodynamics, QED, the vacuum isn't truly empty. It's a seething foam of virtual particles that pop in and out of existence. Under a magnetar's field, these virtual particles become polarized, meaning the vacuum itself behaves like a material, a birefringent medium that can bend and split light. This was once only a theoretical prediction. But in 2016, observations of a neutron star called RxJ 1856.5-3754 provided the first real-world hint that it's true. Light from the star showed an unusual polarization pattern, exactly as predicted if space around it had been magnetized. In other words, the magnetar's magnetic field was so powerful that it changed the properties of empty space. Even atoms behave differently. At 10 to the 11th power teslas, an atom no longer looks like a little solar system. Its electrons are squeezed into elongated orbits along magnetic field lines, turning the atom into a thin, needle-like structure. Chemical bonding would work differently in such an environment. Even the concept of solid and liquid starts to lose meaning. These effects push physics into a regime that's almost untestable on Earth. Our equations can describe them, but no experiment can yet reproduce them. In a sense, magnetars are natural laboratories for quantum gravity. They combine extreme density, magnetic strength, and curvature of spacetime in one small object. When we study them, we're probing the frontier where general relativity meets quantum mechanics, the two great theories of physics that still refuse to merge. And yet, even with these colossal numbers, magnetars remain fragile in their own way. Their magnetic fields decay over time, typically in about 10,000 years. As the field decays, energy is gradually released as heat and radiation, and the once violent magnetar cools and dims. This decay is one of the great puzzles of astrophysics. How exactly the magnetic energy dissipates, whether through crustal fractures, particle emission, or magnetic reconnection, is still under study. But what's clear is that magnetars live fast and fade quickly, burning through their magnetic energy like cosmic fireworks. Let's consider what that field means for the structure of the star itself. The magnetic field acts like invisible tension lines threading through the neutron star's matter. In some regions, these lines can become twisted or tangled, storing additional energy, a bit like a coiled spring. When they suddenly snap back into a lower energy state, the release produces a burst of radiation. This is the leading theory behind magnetar flares. The crust shifts, the field rearranges, and the stored magnetic energy bursts outward. The crustal movements also produce vibrations, oscillations that can last for seconds after a flare. In 2004, after the giant flare of SGR 1806-20, astronomers detected quasi-periodic oscillations in the X-ray light, thought to be the ringing of the neutron star's surface, the literal vibration of a star's crust after it cracked. It's one of the few times we've heard the sound of a starquake, recorded not in air but in light. Every one of these details challenges our intuition about what matter can do. How can something so small hold so much energy? How can magnetism, a force we encounter in simple school experiments, become a destructive engine of cosmic power? Part of the answer lies in scale. Magnetism is a side effect of electromagnetism, one of the four fundamental forces of nature. Its strength doesn't depend on mass, but on charge and motion. So when you compress a star's worth of charged particles into a tiny space, the potential for magnetic intensity grows exponentially. It's a perfect storm of physics. Extreme density, rapid rotation, and turbulence all conspiring in a few seconds to create a magnetic monster. But part of the mystery is philosophical. Magnetars show us that the universe is capable of excess, of creating conditions far beyond what seems necessary or even reasonable. Nature doesn't merely stop at what's efficient, it explores the edges of the possible. And in those edges, we glimpse the raw beauty of physical law, not just as mathematics, but as art written in magnetism and light. Every magnetar is a contradiction. A dead star that still pulses with impossible energy, a small thing with infinite reach. Its field lines may stretch thousands of kilometers into space, shaping the environment around it, accelerating particles, sculpting radiation. It is a reminder that the universe's most profound forces often operate in silence, invisible but absolute. And yet, for all our equations and models, magnetars still keep their secrets. How exactly does that dynamo saturate so quickly? What governs the limit of their field strength? Why do some neutron stars stop at pulsar while others leap into this realm of impossibility? Perhaps it's random chance, or perhaps there's a subtle law we haven't yet seen, something hidden in the turbulence of a dying star. For now, all we can do is listen to their signals, the flashes and pulses from thousands of light years away, and imagine the physics playing out inside that tiny, impossible sphere. Because somewhere out there, beyond the clouds of gas and dust, a star has just died. Its core is collapsing at 1/4 the speed of light, its matter crushed into neutrons, its rotation spinning like a blade of gravity itself. And in that collapse, as electric currents coil and twist, a magnetic field is being born, one that will soon reshape the vacuum, crack the crust, and light up the galaxy in bursts of invisible fire. That, in essence, is the physics of the impossible, a moment where electricity, gravity, and quantum law all converge, and the universe produces something that should not exist, yet does. Every star has its temperament. Some shine steadily for billions of years, others erupt in death throes of flame. But magnetars, those compact, volatile relics of supernovae, have a personality unlike anything else in the cosmos. They are the drama queens of the neutron star family, the ones that can't sit still. They twist, crack, flare, and scream across the electromagnetic spectrum. When they act up, entire detectors in orbit around Earth go momentarily blind. For the most part, they appear quiet, faint points of X-ray light hidden among the constellations. Then, without warning, they detonate with such fury that every satellite designed to monitor gamma rays turns its gaze in shock. These explosions are brief, sometimes just a fraction of a second, yet they release more energy than the combined output of all the stars in our solar neighborhood during that time. The story of how we first discovered these cosmic tantrums began not in a telescope observatory, but in orbit, with instruments designed for war. On March 5th, 1979, several spacecraft, including NASA's Helios 2, the Soviet Venera 11 and 12 probes, and 2 American Vela satellites, suddenly detected an immense flash of gamma radiation sweeping through the solar system. The Vela satellites had been built for a very different purpose, to monitor compliance with nuclear test bans. They were meant to catch secret detonations on Earth, not cosmic ones. But the signal they saw that day was like nothing from any weapon. In just 0.2 seconds, the burst released more energy than the sun emits in 1,000 years. The detectors saturated. Then, after that blinding flash, something even stranger happened. A perfectly regular pulsing of gamma and X-rays, repeating every 8 seconds. Astronomers traced the source to the outskirts of the Large Magellanic Cloud, a small satellite galaxy of the Milky Way, roughly 163,000 light-years away. They designated it SGR 0526-66, the first known soft gamma repeater. Soft referred to the fact that the burst photons had slightly lower energy than those from classic gamma-ray bursts, but make no mistake, they were still extraordinarily violent. This event marked the first time humanity witnessed the temper of a magnetar, though the term itself wouldn't be coined until 1992 by Duncan and Thompson. The phenomenon had already announced itself, a dead star flaring with the force of 1 billion nuclear bombs in less than a heartbeat. The repeating nature of the pulses was the first clue that the source was a rotating object, a neutron star. Each pulse corresponded to one rotation of the star, as if its beam of high-energy radiation were sweeping across space like the light of a cosmic lighthouse. But unlike normal pulsars, which spin dozens or hundreds of times per second, these new objects turned much more slowly, every few seconds. That sluggish pace was a hint that something was breaking them, bleeding away their rotational energy far faster than normal neutron stars. And the culprit was magnetism itself. In a neutron star, the magnetic field is anchored deep within the crust and core. As the star spins, those magnetic field lines twist and drag against surrounding space, accelerating charged particles outward along the magnetic poles. This creates a continuous outflow of energy, an electromagnetic wind. Every rotation, a bit of the star's angular momentum is carried away by this wind, gradually slowing the spin. The rate of slowdown depends on the strength of the magnetic field. Ordinary pulsars lose rotational energy slowly, their fields around 10 to the power of 8 Teslas. But in a magnetar, where the field may reach 10 to the 11th power Teslas, the braking effect is thousands of times stronger. That's why magnetars typically rotate once every 2 to 12 seconds, leisurely by neutron star standards. Each rotation period lengthens over time as the magnetic field saps kinetic energy. It's as though the star is dragging its own invisible anchor through space. Within a few thousand years, a magnetar that began its life spinning hundreds of times per second can slow to a near standstill, yet its magnetism remains ferociously alive. This constant braking also converts rotational energy into heat, which helps sustain the magnetar's glowing X-ray emission long after its birth. Even without flaring, a magnetar shines faintly in X-rays, powered not by fusion, but by magnetic decay. It is, in a sense, a cosmic ember still warm from its creation. After the 1979 event, astronomers began to recognize that SGR 0526-66 was not alone. More bursts appeared in the following decades from other points in the sky: SGR 1806-20, SGR 1900 plus 14, SGR 1627-41. Each source displayed similar behavior, sudden, intense flashes of gamma and X-rays separated by long periods of quiescence. They became known collectively as soft gamma repeaters, or SGRS. At the same time, another mysterious group of objects emerged: anomalous X-ray pulsars, or AXPS. These stars pulsed steadily in X-rays, but their emission was too strong to be explained by rotational energy alone. Unlike ordinary pulsars, which shine because they lose kinetic energy as they spin down, these objects were emitting more X-rays than their rotation could possibly power. For years, scientists treated SGRS and AXPS as distinct classes, until the early 2000s, when the connection became clear. Occasionally, an AXP would enter an outburst phase, behaving exactly like a soft gamma repeater. The two were the same species, showing different moods of the same underlying phenomenon, the magnetar. Today, we know of about 30 confirmed magnetars in our galaxy and its neighbours. They are rare. Perhaps 1 in every 10 neutron stars is born as a magnetar, but their outbursts make them impossible to ignore. So what actually causes these bursts? How can a single star unleash energy comparable to billions of nuclear bombs in less than a second? The answer lies in the delicate, dangerous tension between the magnetar's magnetic field and its solid crust. Imagine the star's crust as a rigid shell only about 1 kilometre thick, floating atop a sea of superfluid neutrons. The magnetic field lines thread through this crust like steel cables through concrete. Over time, as the magnetic field evolves and tries to rearrange itself, those cables shift and twist. The crust resists until it can't. When the strain exceeds the material's breaking point, the crust cracks. This sudden rupture is a starquake. The motion of the crust reconfigures the magnetic field, snapping and reconnecting the lines of magnetic force. This process, called magnetic reconnection, is the same phenomenon that powers solar flares on the sun, but in a magnetar it happens under far more extreme conditions. When reconnection occurs, the magnetic field lines break apart and reconnect in a new configuration, releasing stored magnetic energy into the surrounding plasma. Charged particles are hurled outward at relativistic speeds, generating powerful radiation across the X-ray and gamma-ray spectrum. The result is a flash, a burst that may last only a tenth of a second, yet releases around 10 to the power of 36 joules of energy. To put that in perspective, a single magnetar flare can release as much energy as 1 billion trillion nuclear bombs. It can briefly outshine all other X-ray sources in the galaxy combined. If a flare like that occurred within a few dozen light-years of Earth, it could disrupt our planet's atmosphere. And yet, the process is governed by the same physics that drives the small magnetic storms on our Sun. Its magnetism simply pushed to its absolute limits. The March 5th, 1979 event remains one of the most studied bursts in astrophysical history. After the initial spike, which released as much energy as the Sun does in 10,000 years, the radiation decayed in a repeating 8-second rhythm for several minutes. That pulsing afterglow was the first observational fingerprint of a magnetar's rotation. At the time, scientists had no word for such an object. The concept of a magnetar would not appear for another 13 years, but the clues were all there. The periodic pulses implied a rotating neutron star. The energy output was far too high for a normal pulsar. The soft gamma spectrum suggested magnetic processes, not accretion or black hole activity. Today, SGR 0526-66 is quiet, nestled within the supernova remnant N49 in the Large Magellanic Cloud. Its flare has long since faded, but the ghost of that event lingers in the expanding nebula around it, a cloud still glowing with the memory of a magnetic cataclysm. Most of the time, a magnetar exists in a steady, though uneasy state. It emits persistent X-rays powered by magnetic field decay. Its rotation slowly drifts toward longer periods as magnetic braking saps energy. The field lines gradually rearrange themselves inside, transferring stress to the crust. Every so often, this slow evolution crosses a threshold. A localized region of stress snaps, and the star flares. Smaller microquakes can cause subtle increases in X-ray brightness, while larger fractures produce dramatic outbursts. During a major event, the Magnetars surface can heat to tens of millions of degrees, emitting radiation bright enough to momentarily rival an entire star cluster. The light curve of a flare typically shows an incredibly fast rise, milliseconds, followed by a slower decay over seconds or minutes. This pattern reflects the sudden release of magnetic energy and its gradual dissipation as the crust and magnetosphere settle back into equilibrium. Some magnetars, such as one E1048.1-5937, display semi-regular outbursts every few years. Others remain dormant for decades before erupting again. It's as if each one has a unique personality, a different rhythm of magnetic tension and release. The rotational decay of magnetars, their gradual slowing, is another defining characteristic. Every pulse we observe, whether X-ray or radio, arrives slightly later than the one before. This drift tells us how quickly the star's spin energy is being converted into heat and radiation. A typical magnetar might lose 10 to the 30th power joules per second in rotational energy, a staggering rate. The slowdown is measurable over just a few years of observation. We can even estimate the age of a magnetar by comparing its current rotation period with the rate at which it's slowing down. much like deducing the age of a spinning top by how much it has decelerated. Younger magnetars with stronger fields slow faster. As the magnetic field decays over tens of thousands of years, the braking effect weakens. Eventually, the star's spin stabilizes at several seconds and its activity fades. The magnetar enters old age, becoming a faint, slowly rotating X-ray source, a former tempest now whispering softly to the void. The more we study magnetars, the more they seem to blur the line between the mechanical and the mythical. They are machines of physics so intense that they feel like living things, breathing, pulsing, lashing out, then resting again. Their behavior is governed by equations, yet the outcome is strangely familiar. Tension building until it snaps, energy released in fury, followed by silence. It's an almost emotional pattern played out across the galaxy. Each time one flares, we learn a little more about how magnetic fields behave when stretched to their breaking point. We also learn humility. Our own sun, with its occasional solar flares, is a serene version of this madness, a local demonstration of magnetic instability kept within safe limits. But magnetars remind us that the same physics that warms our planet can also tear apart a star the size of a city. For now, these stellar magnets remain distant enough to be only awe-inspiring, not dangerous, yet their energy still reaches us. In signals caught by space observatories, in brief flashes of X-rays recorded by satellites, in tiny disturbances rippling through the cosmos. Somewhere, right now, a magnetar may be cracking its crust, unleashing a pulse of energy that will travel for tens of thousands of years before it reaches Earth. When it does, it will arrive as a fraction of a second of invisible light, a whisper from a star that exploded long before humans walked the Earth, a reminder that even death in the universe is not the end, but an ongoing conversation. And as we continue listening, we begin to recognize patterns, connections between these magnetic outbursts and another mystery still puzzling astronomers today: sudden, millisecond-long radio flashes known as fast radio bursts. Some believe they're magnetars calling across the cosmos in another wavelength, another mood, another voice, but that's a story for another night. On the morning of December 27th, 2004, as much of the world was still resting in the quiet calm between Christmas and the New Year, something extraordinary and almost unimaginable happened in the depths of space. Without warning, a star thousands of light years away unleashed the most powerful flash of energy ever recorded from beyond our solar system. For just a fraction of a second, it became the brightest object in the sky, brighter than all other sources of X-rays and gamma rays combined. If the source had been only a few light-years closer, Earth might not have escaped unharmed. But we were lucky. We were watching from a safe distance, more than 50,000 light-years away, on the opposite side of the Milky Way. That star was SGR 1806-20, and the event would become known as the 2004 Giant Flare, or, more poetically, the Christmas Explosion. SGR 1806-20 resides in a region of the galaxy called the Sagittarius Arm, shrouded in thick clouds of gas and dust near the constellation of Sagittarius. It's invisible to the naked eye, yet it has been on astronomers' radar since the 1980s as one of the most active magnetars known. Even before 2004, it had shown signs of instability. Small bursts, flashes of X-rays, occasional irregular pulses, but nothing could have prepared us for what it was about to do. At 21:30 Universal Time, satellites across the solar system suddenly registered a colossal surge of gamma radiation. Detectors aboard Swift, RHESSIINTEGRAL, Conus Wind, and dozens of others were blinded, their sensors overwhelmed by the incoming flood of energy. Even spacecraft orbiting Mars and the Moon recorded it. Within milliseconds, every gamma-ray monitor in operation lit up with the same signal, an intense spike followed by a gradual decay. It was as though the universe itself had flashed a cosmic camera bulb. The initial pulse lasted less than 0.2 seconds, yet released about 10 to the power of 39 joules of energy, roughly the same as if the sun had emitted its entire 100,000-year output in one instant. That's a billion trillion tons of TNT exploding simultaneously in a single star no larger than Manhattan Island, and that was just the beginning. After the initial flash, the magnetar continued to pulse rhythmically every 7.56 seconds, corresponding to its rotation period. Each pulse was weaker than the first, gradually fading over the next several minutes as the magnetic field and crust settled back into place. This pattern was eerily similar to the March 5th, 1979 event from SGR 0526-66, but magnified to an almost absurd degree. It was, quite simply, the most luminous stellar event humans had ever observed that didn't involve a supernova or black hole. To grasp the power of that outburst, consider this. If SGR 1806-20 had been located just 10 light-years away, still outside the solar system but within our galactic neighbourhood, its radiation would have stripped away Earth's ozone layer within seconds. Our planet's surface would have been bombarded by ultraviolet light for months. At just 1 light-year, the burst might have sterilized the upper atmosphere entirely. At a few tenths of a light-year, it would have scorched the surface. Fortunately, the star's actual distance, about 50,000 light-years, was enough to reduce its fury to a harmless but awe-inspiring spectacle. Yet even from that enormous distance, the effects were measurable. The wave of gamma radiation reached Earth 0.13 seconds after it left the Moon, fast enough that the light reflected from the lunar surface registered as a faint echo on satellite detectors. For the first time, astronomers recorded a cosmic explosion not only directly, but also through its reflection from our celestial neighbour. The Moon had briefly acted as a mirror for one of the most powerful events in the universe. The radiation slammed into Earth's ionosphere, the upper layer of our atmosphere, where solar radiation normally keeps gases ionized. For a few moments, it was as if the planet had been struck by a second sun, one made of gamma rays instead of light. Instruments designed to monitor the ionosphere for solar flares went wild. They detected sudden, massive disturbances, fluctuations in radio wave propagation, and spikes in atmospheric ionization, unlike anything ever seen from a celestial source outside the solar system. Even the Earth's magnetic field trembled. Magnetometers registered subtle shifts as the incoming energy interacted with the planet's magnetic bubble, briefly compressing it. Radio astronomers noticed shortwave signals around the world fading or vanishing, disrupted by the flood of ionized particles. For those few seconds, the quiet hum of Earth's magnetosphere, normally dominated by the sun, was overtaken by a star on the far side of the galaxy. And then, silence. The pulse was over. The planet settled back into equilibrium. The instruments calmed, and humanity was left staring at the data, astonished. When the numbers were analysed, scientists realised they had witnessed something unprecedented. The energy released in that brief explosion was greater than the total output of all the stars in the Milky Way during the same instant. The flare's luminosity, its brightness per unit area, reached 10 to the 47th watts, a value so high that for a split second, SGR 1806-20 outshone the entire visible universe in gamma rays. The only explanation that fit was a magnetar giant flare, a rare and violent event caused by catastrophic rearrangements of a magnetar's magnetic field. It's thought that the intense internal magnetic pressure, twisting and shifting over centuries, finally overcame the rigidity of the crust. When that crust cracked, the magnetic field lines snapped and reconnected, a process of magnetic reconnection similar to what powers solar flares, but vastly more powerful. The energy stored in the star's magnetic field, enough to power a galaxy for a moment, was released all at once. In essence, a single fracture in a 10-kilometre star sent a wave that reached halfway across the Milky Way. Astronomers had long predicted such an event might occur, but none had ever been observed so clearly. The 2004 flare not only confirmed the Magnetar model beyond reasonable doubt, it reshaped the entire field of high-energy astrophysics. In the months that followed, data poured in from dozens of instruments around the world. Each had caught a different piece of the puzzle. NASA's RHESSI satellite, designed to study solar flares, had been blinded for several seconds. The Integral Observatory recorded the event even through its shielding. The cluster spacecraft orbiting Earth to study its magnetic environment detected the event's effects directly on the magnetosphere, and the Geotail satellite, stationed between Earth and the Moon, captured the faint reflected echo from lunar dust. These cross-confirmations allowed scientists to reconstruct the sequence with astonishing precision. The initial spike, less than 1/5 of a second long, carried nearly all the energy. Then came the pulsating tail, lasting several minutes, modulated by the Magnetar's spin. Each pulse gradually weakened as the star cooled and the magnetosphere settled. But even hours later, X-ray telescopes continued to detect a faint afterglow as the surrounding gas re-radiated the energy. In that single event, astronomers had more data about magnetars than in all previous decades combined. The 2004 giant flare provided the first direct evidence that magnetars could indeed produce the soft gamma repeater behavior predicted by Duncan and Thompson's 1992 theory. It also confirmed that magnetic reconnection, not accretion or nuclear reactions, was responsible for these titanic outbursts. The extreme regularity of the post-flare pulses matched the star's rotation period, solidifying its identity as a slowly spinning neutron star rather than a black hole or exotic object. The event also had an unexpected consequence. It forced scientists to reconsider the origins of another long-standing mystery: short gamma-ray bursts. Before 2004, these bursts, flashes lasting less than 2 seconds, were often attributed solely to collisions between neutron stars. But the SGR 1806-20 flare proved that magnetars could mimic such events when seen from far away. If this flare had occurred in a nearby galaxy instead of our own, it would have looked exactly like a short gamma-ray burst. This realization revolutionized the classification of cosmic explosions, showing that some of the extraterrestrial bursts recorded by past missions were likely magnetars masquerading as other phenomena. In one brief night, a single star had rewritten our understanding of cosmic violence. Even more striking was the human dimension of the discovery, because the flare occurred just one day after the devastating Indian Ocean tsunami of December 26, 2004, its timing was eerily poignant. News of another global-scale event, this one from deep space, spread quickly among scientists, though the general public never felt its effects. While one wave had crossed the oceans of Earth, another, far greater, had swept silently through the fabric of space-time, touching our planet in the form of invisible light. For astrophysicists, the event was a reminder that the universe is not static or serene, but alive with unimaginable power, and that even in our galaxy's quiet corners, there are titans waiting to awaken. The 2004 flare also deepened our understanding of how magnetars evolve. After the explosion, astronomers monitored SGR 1806-20 closely. Its rotation slowed measurably, suggesting that the flare had expelled a massive quantity of plasma into space, effectively increasing the star's magnetic drag. The magnetic field, once tightly wound, had relaxed slightly, but the scars of that rearrangement were visible in the data. In X-rays, the star glowed for months, cooling slowly from its outburst. The crust, once shattered, likely re-solidified in a new configuration, locking in new magnetic stresses that may one day produce another giant flare. If you could somehow stand near that star, if it were even possible to stand in such a place, you would see a small, dark sphere surrounded by rings of trapped plasma and radiation. The magnetic field would be so strong that space itself would appear distorted, shimmering as light bent through the magnetosphere. Every few seconds, a pulse of X-rays would flash from the poles, sweeping across the galaxy like a rotating beacon. And somewhere, thousands of light years away, our tiny blue planet would record the echo of its heartbeat. What made the 2004 explosion so pivotal wasn't just its scale, but its clarity. For the first time, we saw every phase of a magnetar flare in exquisite detail. The initial rupture, the pulsating tail, the interaction with our planet's magnetic field. It transformed magnetars from theoretical curiosities into tangible astrophysical laboratories, places where the laws of physics could be tested under pressures and energies we could never recreate on Earth. Even 2 decades later, the data from that day continues to yield new insights. Astrophysicists still analyze it to refine models of magnetic reconnection, crustal fracture, and the behavior of matter in fields exceeding 10 to the 11th power Teslas. It remains the benchmark against which every other magnetar flare is compared. In a poetic sense, the 2004 giant flare was the moment when the universe reminded us that the line between creation and destruction is thin. A single crack in a dead star's crust unleashed more energy than all the life-giving light of a galaxy. And yet, from that violence, knowledge bloomed. Our understanding of the cosmos deepened. The explosion didn't just light the sky, it illuminated our ignorance, showing us where to look next. The next time you look up at the winter sky, perhaps around the same date in December, remember that somewhere out there, in the dark beyond Sagittarius, a tiny, invisible star once screamed across the galaxy with the brightness of 1 trillion suns. Its light touched our moon, our atmosphere, our instruments, and for an instant every layer of our world responded. A magnetar had announced itself. And in doing so, it changed the way we see the universe, not as a cold expanse of silence, but as a place alive with restless energy, where even the smallest of stars can shake the cosmos awake. Imagine holding a city in your hand, its entire mass, its buildings, its air, its oceans, compressed into a single teaspoon. Now multiply that by 1 billion, and you have the density of a magnetar. To understand these stars, we have to go beneath their fiery tempers, below the bursts and flares, and look inside, to the layers that make up one of the most extreme objects in the universe. On the outside, a magnetar looks calm. A small, smooth sphere, about 20 kilometers wide, barely larger than a city. But beneath that deceptively simple surface lies a structure so alien that even our most advanced physics struggles to describe it. Matter, as we know it, simply doesn't behave this way anywhere else. A neutron star, and by extension a magnetar, is divided into layers: the crust, the outer core, and the inner core. Each layer is governed by a different balance of quantum forces, pressure, and magnetic energy. It's like peeling back the layers of reality itself, each one stranger than the last. Let's begin at the surface. The outer crust of a magnetar is only about 1 kilometer thick, but it's the densest solid known to exist. The top few centimeters may consist of ordinary atomic nuclei, iron and nickel, suspended in a sea of electrons. Here, the magnetic field dominates the behavior of matter. It forces atoms into elongated shapes, stretching them into cylinders aligned with the field lines. The strong field squeezes the electron clouds, compressing atomic orbitals until the difference between atom and nucleus begins to blur. Just a few meters below the surface, the pressure has already crushed atoms entirely. Electrons have been stripped from nuclei and roam freely, forming what physicists call a degenerate electron gas, a kind of subatomic soup where quantum pressure, not thermal motion, keeps the matter from collapsing further. It's cold in temperature, but hot in density, a paradoxical state where solid and plasma lose their meaning. Deeper down, at densities exceeding 10 to the 14th kilograms per cubic meter, nuclei themselves start to deform. They are squeezed so tightly that neighboring nuclei begin to touch. At this point, matter enters one of the strangest phases ever theorized, the nuclear pasta phase. Nuclear pasta might sound whimsical, but it's one of the most serious topics in neutron star physics. The term was coined in the 1990s when physicists realized that, under extreme pressure, nuclear matter doesn't remain uniform. Instead, it arranges itself into complex geometric patterns, long filaments, flat sheets, and even three-dimensional networks, as protons and neutrons fight between the opposing forces of nuclear attraction and Coulomb repulsion. At slightly lower densities, the nuclei form rod-like structures known as spaghetti. Go deeper, and they flatten into broad layers called lasagna. Deeper still, the matter forms gnocchi, bucatini, and cheese-like phases, each representing a different compromise between the short-range nuclear force pulling particles together and the long-range electrostatic force pushing them apart. It's nature's way of packing matter as efficiently as possible before giving up and collapsing into uniform nuclear fluid. These bizarre shapes aren't just theoretical decorations, they have consequences. The nuclear pasta layer influences how heat and magnetic fields move through the star. Its tangled structure can trap or redirect electrons and magnetic flux, potentially explaining the irregularities in a magnetar's spin-down and burst activity. It may also be responsible for the incredible elasticity of the crust, allowing it to store stress until it cracks, causing the starquakes we observe as X-ray flares. Beneath the pasta layer lies the outer core, extending to a depth of about 10 kilometers. Here, the density surpasses 10 to the 17th kilograms per cubic meter. That's 100 trillion times denser than water. In this regime, atomic structure ceases to exist. Nuclei have dissolved into a continuous sea of neutrons, with a small fraction of protons and electrons mixed in. This is a quantum superfluid, a form of matter that flows without resistance. It's as if friction itself has been outlawed. Neutrons in the outer core pair up in a way similar to electrons in superconductors, forming Cooper pairs that move collectively. Meanwhile, the tiny fraction of protons may form a superconducting fluid, carrying electric current without loss. Together, these fluids create a dynamic dance of quantum behavior on a stellar scale. Within this superfluid core, the magnetic field behaves in extraordinary ways. Because the protons form a superconductor, magnetic field lines are confined to narrow tubes, fluxoids, threading through the fluid like invisible wires. Each fluxoid carries a quantized packet of magnetic flux, and as the star rotates, the neutron superfluid forms quantized vortices aligned with the rotation axis. The interaction between these vortices and fluxoids may explain the sudden changes in rotation speed, called glitches, occasionally observed in neutron stars. A glitch occurs when the vortices pin and unpin abruptly, transferring angular momentum between the superfluid core and the crust. In a magnetar, these events might also disturb the magnetic field, triggering bursts or subtle changes in X-ray output. In this region, the matter is so dense that the average spacing between neutrons is about the same as the diameter of a proton. You could think of it as a gigantic atomic nucleus, the entire star acting as one cohesive nuclear-scale object. And then there's the inner core, the deepest and most mysterious layer of all. Here, the density may exceed 5 times that of normal nuclear matter, approaching conditions similar to those that existed microseconds after the Big Bang. What lies inside remains one of the biggest open questions in astrophysics. At such densities, neutrons might begin to break down into their constituent quarks, up, down, and strange, forming an exotic fluid known as quark matter or strange quark matter. If true, then deep within every magnetar there may be a drop of the primordial soup from which all matter in the universe once emerged. Some theories suggest the existence of hyperons, particles containing strange quarks bound with neutrons, appearing in the inner core as pressure rises. Others propose a mixed phase, where regions of hadronic, normal nuclear matter coexist with pockets of deconfined quarks, forming an intermediate state between neutron and quark star. The exact equation of state, the relationship between pressure, density, and temperature in this environment, is still uncertain. Even our most sophisticated models of nuclear physics begin to falter here. A few researchers speculate that in extreme magnetars, the magnetic field itself might influence this transition. Fields of 10 to the 11th Teslas can alter the energy levels of subatomic particles, potentially favoring certain quark configurations over others. If so, the magnetic field might determine not only the magnetar's surface activity, but also its internal composition, a connection between the smallest particles and the largest explosions in the cosmos. As if that weren't strange enough, the magnetar's ultra-strong magnetic field transforms not just matter, but space itself. Quantum electrodynamics, QED, predicts that at field strengths above about 10 to the power of 9 Teslas, the vacuum becomes polarized, meaning that empty space starts acting like a material medium. This effect, called vacuum birefringence, causes light to split into two polarization modes, each traveling at slightly different speeds. In simpler terms, even nothingness becomes optical glass. Photons moving through this magnetized vacuum can be bent, slowed, or even converted into particle pairs. The space around a magnetar behaves like a lens sculpted by magnetism rather than gravity. In 2016, the European Southern Observatory observed this effect for the first time, studying a neutron star known as RxJ 1856.5-3754. The polarized light from that star showed precisely the signature expected if the vacuum around it had become birefringent, confirming one of QED's most exotic predictions. In magnetars, this effect is expected to be even stronger. It means that when we observe a magnetar's light, we're not just seeing the star itself, we're seeing the universe distorted by the star's magnetism. Every photon carries within it the fingerprint of an altered vacuum. Even the geometry of the magnetar's crust and core may be shaped by magnetic stress. The internal field can deform the star slightly, making it oblate or prolate depending on how the field lines thread through it. This deformation might produce tiny ripples in space-time, gravitational waves, whenever the field rearranges or the crust cracks. Although these signals would be weak, future gravitational wave detectors might one day catch them, providing a direct probe of the star's interior. In the outer crust, meanwhile, the immense field controls how heat escapes. Because electrons can only move easily along magnetic field lines, heat conduction becomes anisotropic, much faster along the poles than across the equator. This could explain why many magnetars appear to have hot spots on their surfaces, areas that glow brighter in X-rays. It's as if the star's magnetic skeleton is channeling its own warmth. The crust itself might be only a few centimeters thick in some regions, stretched and thinned by magnetic tension. When these areas finally give way, they release bursts of radiation, not unlike tectonic plates releasing an earthquake's stored energy. But instead of stone cracking under pressure, it's a lattice of degenerate nuclei breaking under magnetism. If we could somehow slice open a magnetar, the transition from surface to core would be unlike anything seen elsewhere in the cosmos. You'd start with iron and nickel in an electron sea, recognizable if extreme. Then you'd fall into a jungle of nuclear spaghetti and lasagna, where matter bends itself into geometric knots. Deeper, you'd wade through a superfluid ocean of neutrons and superconducting protons, shimmering with quantized vortices. And finally, at the heart, you'd encounter something beyond human comprehension, a soup of quarks or hyperons, dense enough to make atomic nuclei meaningless. Each layer follows the same laws of physics, yet each bends them almost to breaking. Together, they form a single, self-consistent object, a star where gravity, quantum mechanics, and electromagnetism all share control in a perpetual truce. The deeper we study magnetars, the more they challenge our confidence in knowing what matter even is. We're used to thinking of the universe as made of familiar building blocks, atoms, protons, neutrons. But magnetars remind us that those structures are fragile, and that under enough pressure and magnetism, even the laws that govern them begin to shift. In that sense, these stars are not just astrophysical curiosities, they are laboratories for the fundamental forces of nature, places where we can test our theories about how particles behave, how fields interact, and where the limits of known physics might give way to something new. Every pulse of X-rays, every sudden flare, every slow cooling curve is a message from within that impossible interior. A coded transmission from a world where the boundaries of physics dissolve and new rules take shape. And perhaps, in studying those messages, we'll find clues not only to how stars die, but how matter itself is built, from the spaghetti strands of nuclear pasta to the quark soup at the heart of creation. They are few, but they are unforgettable. Across the Milky Way, hidden in distant star-forming regions and cloaked behind clouds of gas and dust, a few dozen tiny stars shine with impossible power. They do not burn like normal suns. They do not live or die as others do. They flash, whisper, and pulse, brief, erratic signals of unimaginable energy, each one a heartbeat from a corpse, each one a reminder that even after death, a star can still roar. We call them Magnetars, and though we found only around 30 of them, they've already reshaped our understanding of what a star can be. Each has its own personality, its own rhythm, brightness, and quirks, but together they form a family of magnetic monsters scattered across the galactic sky. The best known of them all is SGR 1806-20, the one that gave us the 2004 Christmas explosion, the brightest burst ever detected beyond the solar system. It lies about 50,000 light-years away, in a dense region of the Milky Way known as the Sagittarius Arm, embedded in the star cluster CL 1806-20. Surrounding it are some of the most massive and luminous stars in our galaxy, including the blue hypergiant LBV 1806-20, one of the largest known. That neighbourhood tells us something. Magnetars are often born from the most massive stars, giants that live fast and die young. Even now, long after its famous outburst, SGR 1806-20 remains active, emitting bursts of X-rays and softer gamma rays from time to time. It spins once every 7.56 seconds, an eternity compared to ordinary pulsars, which can rotate hundreds of times per second. Its rotation slows steadily as magnetic braking drains energy away, and its surface field, around 2 × 10 to the 11th power Teslas, makes it one of the most magnetic objects ever measured. When it flares, the entire magnetosphere, the invisible cocoon of field lines surrounding the star, ripples and rearranges, releasing energy that travels tens of thousands of light years through interstellar space. To astronomers, it's not just a celestial event, it's a natural experiment in magnetism, one that no laboratory could ever replicate. Another well-studied example is one E10 to the power of 48.1 to 5,937, located about 9,000 light-years away in the constellation Carina. Discovered in 1980 by the Einstein Observatory, it became one of the first objects identified as an anomalous X-ray pulsar, AXP, long before the connection to magnetars was understood. Unlike SGR 1806-20, which produces rare but spectacular giant flares, one E1048.1-5937 is restless. It experiences smaller outbursts every few years, bursts of X-rays that brighten it by a factor of 10 or more. It spins once every 6.45 seconds, and its magnetic field is estimated at roughly 3 × 10 to the 10th power Teslas, still thousands of times stronger than any pulsar. What fascinates astronomers about 1E10 to the 48.1 to 5937 is its unpredictable behaviour. Its X-ray brightness rises and falls without warning. Its rotation slows, then speeds up slightly, then slows again. Sometimes its pulse shape changes, suggesting rearrangements in its magnetic field or crust. In a way, it's the moodiest of the magnetars, a star with weather, and studying it helps scientists understand how internal magnetic stresses evolve over time and how the decaying field affects the emission we see. Then there's SwiftJ 1818.0 to 1607, discovered much more recently in March 2020. This newcomer startled astronomers with its youth and unusual mix of traits. It was found by NASA's Swift satellite during a sudden X-ray outburst and quickly identified as a magnetar because of its magnetic strength, about 10 to the 11th power Teslas, and its pulse period of just 1.36 seconds, making it the fastest spinning magnetar ever recorded. Even more surprisingly, Swift J1818.0-1607 emits radio waves, behaving at times like an ordinary pulsar. This crossover, a magnetar that also shines in radio, blurs the boundary between these two categories of neutron stars. It hints that the line separating pulsar from magnetar isn't as clear as once thought. Perhaps they are stages of the same evolutionary story, the same object under different magnetic moods. Swift J1818's discovery also reminded astronomers how dynamic these objects can be. Within weeks of its first detection, it faded dramatically in X-rays, cooling rapidly as the flare energy dissipated. That rapid evolution gave scientists a rare chance to watch a magnetar settle back into dormancy, the afterglow of a magnetic storm cooling before their eyes. Other names fill the magnetar catalogue, each with its own mysteries. SGR 1900+14, famous for its massive 1998 flare that briefly ionized Earth's atmosphere. 1E2259+586, nestled within the supernova remnant CTB109, known for its twin-peaked pulses and sudden spin-up glitches. CXOUJ 164710.2 to 455216, a magnetar in the young star cluster Westerland 1, thought to have formed from a progenitor star weighing more than 40 suns, and SGR 1935+2154, which in 2020 produced something extraordinary, a fast radio burst, or FRB, confirming for the first time that magnetars can generate those mysterious millisecond radio flashes that have puzzled astronomers for over a decade. Each discovery widens the spectrum of magnetar behavior. Some emit in X-rays only, some show radio pulses, a few produce both, switching between them unpredictably. Some are relatively steady, others flash like faulty cosmic light bulbs. But behind every variation lies the same core engine, a decaying, shifting, tormented magnetic field twisting itself through a star's crust of nuclear matter. Observing these magnetic monsters is a task that requires the full arsenal of modern astronomy. Magnetars emit mainly in X-rays and gamma rays, wavelengths that Earth's atmosphere blocks, so we study them with space telescopes. The Chandra X-ray Observatory, with its superb angular resolution, can pinpoint a magnetar's exact location and map the surrounding supernova remnant in exquisite detail. Through Chandra's eye, the debris of a star's explosion glows like a halo around the neutron core, revealing the environment that gave birth to it. XMM Newton, the European Space Agency's powerful X-ray telescope, complements Chandra with high sensitivity to faint emissions. It has tracked magnetars for years, measuring how their brightness decays after flares and how their spectra change as they cool. XMM, Newton's long exposures have revealed the subtle heartbeat-like pulses of magnetars, often only a few % variations in brightness repeating every few seconds. Closer to home, the NICER instrument aboard the International Space Station provides rapid timing observations. Its detectors can record X-ray pulses with microsecond precision, allowing scientists to measure tiny irregularities in rotation, the spin-down rates, glitches, and timing noise that reveal the inner turmoil of these stars. When a magnetar suddenly changes its pulse rate or profile, NICER catches the shift almost in real time. At higher energies, the Fermi Gamma Ray Space Telescope monitors the entire sky for bursts. Fermi's Gamma Ray Burst Monitor, GBM, is constantly on watch for the sudden, millisecond-long flashes that magnetars produce. When one appears, Fermi triangulates its position and alerts other observatories instantly, triggering a global response, a cosmic emergency call. Within minutes, XMM, Newton, Chandra, and ground-based radio telescopes can turn toward the source to record the afterglow. This coordination has become the cornerstone of magnetar research, a symphony of telescopes across the electromagnetic spectrum working together to capture a star's scream before it fades. Detecting and analysing magnetar bursts requires both speed and subtlety. The bursts can be as short as a few milliseconds, shorter than the blink of an eye, and often arrive without warning. Satellites equipped with wide-field detectors record these sudden spikes in count rate, often saturating their sensors. Then comes the detective work, cross-referencing which satellites saw the burst first and at what time, using the tiny differences in arrival time to triangulate its location in the sky. This technique, known as interplanetary network triangulation, uses spacecraft spread across the solar system, sometimes including ones orbiting Mars or Mercury, to pinpoint the source within a fraction of a degree. Once localized, X-ray telescopes zoom in to measure the decay. They record the spectral shape, how the brightness changes with energy, to determine the temperature and magnetic field strength. A magnetar flare might start as a black body glow at tens of millions of degrees, then fade into a softer tail of emission as the outer layers cool. Spectral lines, if detected, can reveal the effects of gravitational redshift and magnetic splitting, giving insight into both the mass and field configuration. Even the timing of pulses carries clues. The pattern of bright and dim phases can show whether we're seeing one magnetic pole or both, and whether the beam is being distorted by magnetic lensing. By comparing pulse shapes before and after an outburst, scientists can map how the field geometry changes, how the invisible skeleton of magnetism flexes during a starquake. One of the great puzzles in magnetar research is why their emission patterns differ so much from normal pulsars. A pulsar's beams are typically powered by rotational energy. As the star spins, it accelerates particles along its magnetic poles, generating radio waves and sometimes X-rays. Its power source is kinetic, the gradual loss of spin. That's why ordinary pulsars are so regular. They're essentially rotating dynamos, slowing predictably over millions of years. A magnetar, however, is powered not by rotation but by the decay of its magnetic field. Its energy comes from within, from the slow unwinding of a magnetic labyrinth trapped in its crust and core. Because the field decays irregularly, its emissions are unstable, sometimes surging dramatically as internal stresses shift. That's why magnetars often appear to have erratic or anomalous pulses. Their rotation might remain steady, but their brightness can vary by factors of 10 or 100 overnight. In radio wavelengths, the difference is just as striking. Most pulsars emit narrow, steady beams of radio waves generated by particle acceleration in their magnetospheres. Magnetars, by contrast, emit radio waves sporadically and with strange polarization, sometimes switching on and off, or changing shape completely between observations. Their radio pulses can even show flat spectra, meaning they remain strong across a wide range of frequencies, unlike the steeply decreasing radio power of pulsars. These quirks suggest that magnetar magnetospheres are far more twisted and dynamic. Where a pulsar's field lines are relatively orderly, a magnetar's are tangled and stressed, constantly reconfiguring. This twisting may create enormous electric fields that accelerate particles differently, producing emissions across multiple wavelengths. It also makes magnetars more efficient X-ray sources, since their decaying fields continuously inject energy into the crust and magnetosphere. The result is a spectrum that can include both thermal radiation from the hot surface and non-thermal radiation from magnetic processes above it. When astronomers graph a magnetar's light output across the electromagnetic spectrum, it doesn't form the clean curve of a cooling star. Instead, it's a patchwork, bursts, hums, and tails, as if the star were trying to speak in several languages at once. Over the past 2 decades, these observations have revealed not only the diversity of magnetars, but also their connection to other astrophysical mysteries. Some fast radio bursts, as seen with SGR 1935 +2 154, are now confirmed to come from magnetars. Certain short gamma-ray bursts, once thought to mark black hole mergers, may instead be distant magnetar flares, and a few superluminous supernova explosions brighter than any ordinary one may mark the birth of a magnetar, its spin and magnetic field powering the explosion long after the initial blast. What began as a handful of puzzling soft gamma repeaters has become a web of connections linking magnetars to some of the most powerful phenomena in the universe. They are no longer oddities, they are keystones, the bridge between stellar death, high-energy astrophysics, and the frontier of particle physics. When we map the magnetars of our galaxy, their distribution isn't random. They cluster near the galactic plane, in regions rich with young massive stars. That makes sense. Only the most massive stars leave behind magnetars when they die. Each one is a scar on the sky, a place where a star once lived, burned, collapsed, and was reborn as a magnetized relic of its own destruction. From Earth, we can't see them with our eyes, but with the right instruments, the galaxy comes alive with their flickers. Each pulse, each flare, each whisper of radio static is a signal from a corpse spinning in the dark. And though they are separated by thousands of light years, the story they tell is universal, that even in silence there can be motion, even in death there can be energy. The magnetars we know are just the visible few. There may be hundreds more, dormant, faint, or hidden behind dust, each waiting for its moment to wake, crack its crust, and remind the galaxy that the dead still move. And as our telescopes grow sharper, our detectors faster, and our algorithms more precise, we'll catch more of them in the act. Each one another glimpse into the strangest corners of physics, where magnetism becomes a storm and a star becomes an engine of impossible light. Every so often the universe whispers, not in light or heat, but in radio waves, brief, bright pulses that last for only a few milliseconds, yet release more energy than the sun emits in days. They arrive from random directions, unannounced like cosmic Morse code, each one a message from somewhere far beyond our comprehension. For years, no one knew what they were, who sent them, or even whether they were real. We now call them fast radio bursts, or FRBS, and one of the strongest suspects behind their mysterious origins is a magnetar. The first of these ghostly signals was discovered in 2007, almost by accident. Astrophysicist Duncan Lorimer, working with his student David Narkovich at West Virginia University, was analysing archived data from the Parkes Radio Telescope in Australia. Their goal was routine, to search for pulsars, those rhythmic, predictable radio lighthouses that sweep across our skies. But hidden in the data from July 24, 2001, they found something entirely unexpected, a single, enormous radio pulse that lasted less than 5 milliseconds. It was so intense that it saturated the detectors. What made it extraordinary wasn't just its brightness, but its dispersion, the way radio waves at lower frequencies arrived slightly later than higher ones. This dispersion effect is caused by interstellar electrons, which slow down longer wavelengths more than shorter ones. By measuring it, astronomers can estimate how far the signal has travelled. The delay in that single pulse suggested it came from billions of light years away, far outside the Milky Way. Nothing like it had ever been seen before. They published their findings in 2007, calling it the Lorimer burst after its discoverer. It was so strange that many dismissed it as an instrumental glitch, a satellite reflection, or even microwave interference from the telescope's staff kitchen. But over the next few years, more signals appeared, faint, fast, and scattered across the sky. Each one lasted only milliseconds. Each one defied explanation. It soon became clear the universe was peppered with these invisible flashes, and they weren't rare. Statistically, thousands occur every day. We just happen to catch a tiny fraction. But what could produce such a powerful, coherent blast of radio energy in so little time? Whatever it was, it had to be compact, smaller than a planet, likely smaller than a star, and it had to be capable of releasing colossal amounts of energy almost instantaneously. The list of suspects was short: black holes, neutron stars, or something even stranger. At first, theories flourished wildly. Some suggested the merging of neutron stars, others invoked collapsing black holes or exotic cosmic strings. More imaginative minds proposed alien civilizations broadcasting their presence across the cosmos, a possibility that, while entertaining, faded as the data grew. Then, in the late 2010s, astronomers began noticing patterns. A few FRBs, like FRB 121102, were found to repeat, not regularly but unpredictably. This ruled out catastrophic one-time events like mergers. Whatever produced them had to survive the explosion. It also had to operate within extreme magnetic fields, because the radio waves often showed signs of polarization, twisted as if they had passed through intense magnetism. That pointed toward one candidate above all others, Magnetars. For years, it remained an intriguing hypothesis, but not proof. Then, in April 2020, the universe finally obliged. Astronomers monitoring the Magnetar SGR 1935+2-154, located about 30,000 light-years away in the constellation Vulpecula, detected an outburst of X-rays and gamma rays. Nothing unusual for a magnetar. But just at that same moment, two radio observatories, CHIME in Canada and STARE 2 in the United States, recorded a powerful radio burst unlike any seen from within our galaxy. The two signals matched perfectly in timing. It was the first time an FRB had ever been observed coming from a known object. The event was named FRB 200428 for the date it was detected, April 28, 2020. For the first time, astronomers could say with certainty a magnetar had produced a fast radio burst. The signal wasn't as strong as the extragalactic FRBs we normally detect. After all, SGR 1935+2-154 is only 30,000 light-years away, but if you placed it at the same distance as the Lorimer burst, its apparent brightness would have matched perfectly. It was the missing link everyone had been waiting for. The connection between magnetars and FRBS was no longer speculation, it was fact. So how does a magnetar create a burst of radio energy powerful enough to be seen across billions of light-years? Several mechanisms have been proposed, each plausible, each terrifying in its own way. One involves magnetic reconnection, the same process that powers solar flares, but amplified to magnetar scale. The magnetar's magnetic field lines, twisted and tangled over centuries, can suddenly snap and reconnect, releasing energy equivalent to billions of nuclear bombs. That energy propagates outward through the magnetosphere, accelerating charged particles to near light speed. These particles then emit coherent radio waves, synchronized focused bursts, much like a natural cosmic laser, or in this case, a maser. This could explain the millisecond duration and the brightness of FRBS. Another model focuses on crustal fractures. As the magnetar's intense magnetic field decays and shifts, it stresses the crust. A layer just a kilometre thick, yet strong enough to resist forces that would shatter any material on Earth. Eventually, the strain becomes too great. The crust cracks, sending seismic waves through the star. These waves shake the magnetosphere, producing shocks that can generate short, coherent radio flashes. This mechanism might explain repeating FRBS. The magnetar doesn't destroy itself in each event. It merely shifts and releases a little stress at a time. A third possibility involves magnetospheric shocks. When magnetic energy builds up and releases, it can launch relativistic plasma shells into space. Thin shells of electrons and positrons that race outward. As these shells collide with slower-moving material already in the magnetosphere, the interaction can create a shock front. The shock compresses and accelerates particles, triggering a burst of coherent radio emission. This could produce both isolated and repeating bursts, depending on how frequently the magnetar ejects plasma. All these models share one key feature. The engine is magnetic. The same magnetic energy that drives magnetar flares in X-rays and gamma rays can, under the right conditions, create powerful radio bursts, focused, brief, and intense enough to cross cosmic distances. But the FRB mystery didn't end there. Once magnetars were confirmed as a source, new questions arose. Were they the only source, or just one among many? Some FRBs, like FRB 121102, repeat thousands of times over years, even following semi-regular cycles. Its bursts sometimes last longer and show complex frequency structures. It resides in a dwarf galaxy over 3 billion light-years away, surrounded by a persistent radio nebula, perhaps the remnant of a supernova or magnetar wind. This environment fits perfectly with a young magnetar still shedding energy into the surrounding gas. But others behave differently. Many fast radio bursts appear to occur just once. They don't repeat, at least not on human timescales. Some come from galaxies with old stellar populations, places where massive stars, the progenitors of magnetars, are rare. That suggests multiple origins. Maybe some fast radio bursts come from magnetars, while others arise from neutron star mergers, black hole interactions, or other catastrophic processes. It's even possible that the FRBS we see are a mixture. Young, energetic magnetars producing frequent repeating bursts, while older or rarer events come from one-time collisions. The debate remains lively. Astrophysicists love to argue about FRBS. Some teams model magnetar magnetospheres in supercomputers, simulating crustal fractures and magnetic shocks that produce millisecond radio waves. Others explore more exotic theories, collapsing axion stars, cosmic strings, or black hole magnetospheres. But the 2020 discovery shifted the odds heavily toward magnetars as the primary culprits. What's fascinating is how FRBS seem to bridge the gap between different classes of cosmic phenomena. They connect the relatively nearby magnetar bursts we've known for decades to the mysterious distant explosions that pepper the universe. It's as if magnetars exist on a sliding scale of fury. At one end, gentle X-ray flickers and small bursts. At the other, full-scale radio storms visible across billions of light-years. The 2020 event showed that the same basic mechanism, magnetic energy release, can produce emissions across vastly different scales. A small rearrangement in a magnetar's field might produce a local flare. A larger, more catastrophic one might generate an FRB bright enough to reach another galaxy. In both cases, the engine is the same, the restless magnetism of a dead star. In that sense, FRBS have given us a new language for listening to the universe, where gamma-ray bursts speak of cataclysms, star deaths, black hole births. FRBs speak of something subtler, the ongoing twitching of stellar ghosts, each still crackling with magnetic tension. They also challenge our technology, because FRBS are so brief, catching one requires constant vigilance and rapid coordination. Instruments like CHIME in Canada scan the sky continuously, recording terabytes of data every day. Software algorithms sift through it in real time, looking for patterns that match an FRB's signature, a sharp spike, a dispersion sweep, a characteristic curve. When one is detected, alerts go out across the world within seconds. Telescopes on every continent swing into position to look for afterglows in X-rays, optical light, or even neutrinos. The field has become a global collaboration and a race against time. By the time a burst arrives, it's already over. All we can do is capture its echo, decode its dispersion, and trace it back to the galaxy that birthed it. Each new detection adds another piece to the puzzle. Some fast radio bursts show periodic activity, hinting at precession or binary companions. Some exhibit fine substructure, microbursts within bursts, spaced by microseconds, suggesting multiple emission regions or rapidly changing magnetic conditions. And a few show polarization so extreme that it must have passed through magnetic fields even stronger than we thought possible. Every one of these clues points again and again toward the same conclusion. Magnetism is at the heart of the mystery. The connection between FRBS and magnetars has done more than solve one cosmic riddle. It has opened new ones. It suggests that magnetars are not just local curiosities, but major players in the energy budget of the universe. They might be responsible for shaping the interstellar medium of galaxies, injecting bursts of radiation that ionize gas clouds and accelerate particles. They might even serve as cosmic probes. The dispersion of FRBS tells us about the amount of ionized matter between galaxies, offering a way to measure the otherwise missing baryonic matter of the universe. So a magnetar's tantrum, while brief, becomes a tool for cosmic cartography. By studying these millisecond flashes, we can map the invisible structure of the cosmos, the gas, plasma, and magnetic fields that weave between galaxies. There's something poetic about that. Dead stars lighting the way to understanding the living universe. But one question remains, one that divides the community to this day. Are all FRBS born from magnetars? The safest answer is probably not, at least not all. The diversity in FRB properties, their repetition rates, energies, and host environments hints at more than one origin. Some might indeed come from young, energetic magnetars like SGR 1935 + 2 154. Others could emerge from older magnetars in binary systems, interacting with companions. Still others might come from entirely different processes, the merging of compact objects or the collapse of neutron stars into black holes. But whether they're all magnetars or not, every FRB carries the same underlying message, that the universe is still alive with sudden, unpredictable energy. Even long after the first stars died, their remnants continue to send pulses of light, like cosmic memories flickering across time. And somewhere, perhaps right now, another magnetar is preparing to release one. Its magnetic field is twisting, straining, storing energy beyond imagination. When it finally snaps, a pulse will fly out across the void, a whisper of radio waves that will travel for millions or billions of years before some telescope on a small blue planet hears it. A single millisecond of sound from the grave. A story of creation, destruction, and magnetism written in a burst of radio light. There is a point in nature where even the equations hesitate, where the laws of physics, those neat, dependable tools we use to make sense of the world, start to blur at their edges. A place where theory is no longer enough and imagination must take its place. Magnetars live in that boundary. They are not simply strong magnets. They are demonstrations of what happens when magnetic fields become so intense that they stop being a force and start becoming a fabric, something that reshapes the very space they inhabit. At field strengths of 10 to the 11th Teslas, the magnetism around a magnetar does more than move charged particles. It reaches into the vacuum itself, changing how light travels, how atoms behave, and even how reality defines itself. To understand how a magnetar can break physics, we need to begin with one of the most remarkable theories ever conceived, quantum electrodynamics, or QED. It's the framework that describes how light and matter interact, and it has been tested to an almost absurd level of precision. Every spark, every beam of light, every electron orbiting an atom behaves exactly as QED predicts, at least under ordinary conditions. But ordinary doesn't apply on a magnetar. According to QED, what we think of as empty space isn't truly empty. It's a seething ocean of virtual particles, pairs of electrons and positrons that constantly flicker in and out of existence. They appear and vanish so quickly that we can't observe them directly, but their presence subtly influences everything. They give rise to effects like the Casimir force, and they slightly alter the charge of the electron itself. In a magnetar's magnetic field, these virtual particles are no longer a background hum. They become part of the stage. The field is so strong that it can polarize the vacuum, aligning the dance of virtual particles so that space itself behaves like a crystal. This phenomenon, called vacuum birefringence, means that light traveling through empty space near a magnetar can split into two polarization modes, each moving at slightly different speeds. In other words, light can experience the vacuum as if it were glass, a material medium created entirely by magnetism. That sounds poetic, but it's literal physics. Photons, the quantum particles of light, feel the structure of the vacuum changing. Space itself gains texture. We have actually seen hints of this. In 2016, astronomers observing a neutron star called RxJ 1856.5-3754 detected polarization in its optical light consistent with QED predictions for vacuum birefringence. It was the first experimental evidence that this bizarre effect, once only a line in Feynman's equations, is real. And magnetars take it much further. Around them, the vacuum doesn't just bend light, it may even convert it. When the magnetic field approaches or exceeds 10 to the power of 9 teslas, another exotic QED effect becomes possible: photon splitting. Under normal circumstances, a photon, a single quantum of light, can't simply split into two lower energy photons. That would violate the conservation of energy and momentum in free space. But in a strong magnetic field, the rules change. The field provides the extra momentum needed to balance the equation. So, near a magnetar, a high-energy gamma-ray photon can spontaneously divide into two lesser photons. It's as if light itself fractures under pressure. This process has profound consequences. It could explain why magnetars, despite their tremendous energies, don't always produce as many gamma rays as expected. Much of the energy is lost to photon splitting, a built-in safety valve of nature that prevents runaway gamma ray emission. It also means that the radiation environment near a magnetar is inherently quantum. Every photon, every interaction, is influenced by the interplay between matter, energy, and vacuum. The effect is so extreme that near the surface, even the structure of atoms collapses under it. Imagine an atom, a tiny solar system of electrons orbiting a nucleus. In a laboratory field, even 1,000,000 times stronger than Earth's, those orbits might distort slightly. But at magnetar levels, they are completely reshaped. The magnetic field forces the electrons into tight spirals around field lines, compressing them laterally while allowing them to extend along the direction of the field. The result is that atoms become needle-shaped, elongated structures thousands of times longer than they are wide. In these conditions, ordinary chemistry ceases to exist. The periodic table, that tidy grid of predictable behavior, loses its meaning. Bonding, energy levels, even the color of matter, all are rewritten by the field. If you could somehow scoop a piece of a magnetar's crust and hold it in your hand, ignoring for a moment that it would weigh as much as a mountain, it wouldn't behave like any substance on Earth. Its electrons would move in quantized paths dictated not by the nucleus, but by the surrounding magnetic field. Every atom would be more a filament than a sphere, stretched along invisible magnetic rails. And this isn't limited to matter. The field's influence extends to space-time itself. Because energy curves space and magnetic fields are energy, a sufficiently strong field can subtly distort the geometry of the surrounding region. In general relativity, we're used to thinking of mass as the main source of gravity, but energy and pressure also contribute. In the neighborhood of a magnetar, the stress energy from the magnetic field becomes significant enough to shape the curvature of space-time. The magnetar doesn't just bend space with its mass, it bends it with its magnetism. When you start adding all these effects together, vacuum polarization, photon splitting, atomic distortion, space-time curvature, you begin to see why magnetars are so important to physicists. They aren't just astrophysical curiosities, they are natural laboratories for the breakdown of physical law. Every fundamental theory we have, general relativity, quantum mechanics, electromagnetism, works beautifully in its own domain. But they were never meant to coexist peacefully. In a magnetar, they're forced to. Gravity crushes matter to nuclear densities. Quantum mechanics dictates the behavior of degenerate particles. Electromagnetism grows so intense that it modifies the vacuum itself. It's the ultimate stress test for the universe's architecture. And yet, even our most advanced mathematics struggles to keep up. Simulating a magnetar from first principles, accounting for relativity, quantum effects, and magnetohydrodynamics, remains one of the hardest problems in computational physics. We can approximate, but the full truth remains beyond our reach. It's humbling to realize that the cosmos contains objects that are both real and, in a sense, beyond calculation. Among the more speculative frontiers that magnetars hint at is the possibility of magnetic monopoles, hypothetical particles that carry a single magnetic charge, either north or south, instead of the paired poles we see in every magnet. In classical physics, no matter how many times you cut a magnet in half, you always get two smaller dipoles. North and south are inseparable. But some theories of grand unification, attempts to merge all forces of nature into one, predict that monopoles should exist, though they would be incredibly massive and rare. If such particles are real, they might interact strongly with extreme magnetic fields. A magnetar's magnetosphere could, in theory, trap or even generate monopoles under certain exotic conditions. No evidence for this has ever been found, but the thought lingers. Could these stars, the most magnetic places in the known universe, be the key to discovering magnetic charge in its purest form? Even without monopoles, magnetars force us to think about symmetry, one of the most profound concepts in physics. The laws of nature are built around symmetry. Electric and magnetic fields mirror each other, matter and antimatter balance in equations, particles appear in pairs. But the universe doesn't always respect perfect balance. Symmetry is often broken, and that breaking gives rise to structure, to galaxies, to matter, even to life. In a magnetar, symmetry is broken on an almost moral scale. Magnetism overwhelms everything else. The field's direction defines up and down, inside and outside. Even space behaves differently depending on whether light moves along or across the field. In such a world, the universe ceases to be uniform. It becomes biased, directional, polarized, a canvas ruled by magnetic order. It's as though nature, usually democratic in its forces, allows one to seize control entirely. There's a philosophical weight to this. In magnetars, we see the universe testing itself, probing the edge cases of its own design. Every law we know is still obeyed, but only barely. They hold together by their fingertips, strained but unbroken. It's as if the cosmos wants to know what happens when you turn every dial to its maximum setting. If you look at the hierarchy of cosmic phenomena, stars, black holes, quasars, dark energy, magnetars occupy a curious middle ground. They're not as final as black holes, which swallow their own information, but they're more extreme than any other visible star. They're balanced at the knife edge between stability and collapse. Too much mass, and gravity would win, forming a black hole. Too little, and the magnetic field would never reach such intensity. Somewhere in that narrow window, nature found a configuration that defies both annihilation and normality, a compromise between light and darkness. Are magnetars examples of nature pushing physics to its limit, or are they signposts pointing to something beyond our current understanding? Maybe both. They remind us that impossible doesn't mean non-existent, only that our understanding hasn't caught up yet. When James Clerk Maxwell wrote down his equations for electromagnetism in the 1860s, he couldn't have imagined a place where those equations would need quantum corrections. When Einstein described gravity as geometry, he couldn't have foreseen the places where that geometry would be reshaped by magnetism itself. And when Feynman and Schwinger built QED, they couldn't have predicted stars where the vacuum would behave like a crystal and light would split apart in flight. Yet here we are, with telescopes catching the signatures of exactly those phenomena. Magnetars are not exceptions to physics. They are its full expression, the extreme case that proves the rule and tests it to breaking. In the quiet between their flares, magnetars emit a soft, steady X-ray glow, the hum of magnetic decay continuing over millennia. It's easy to forget that beneath that calm lies a realm where atoms are spaghetti, where space is refractive, and where photons can split like drops of water. Every flicker of their light is a message from the farthest frontier of physics. When we study them, we're not just learning about dead stars, we're learning about the rules that built reality itself. And if someday we find those rules to be incomplete, it will be in places like this, in the hearts of magnetic titans, where the universe dares to do things it never told us were possible. So when you look up at the night sky, remember that somewhere out there spins a sphere of impossible magnetism, small enough to fit in a city, dense enough to anchor a galaxy's worth of questions. Its magnetic field stretches across light years. Its photons emerge from a vacuum that's no longer empty. It's not just a star, it's a riddle that glows, and perhaps that's the ultimate beauty of magnetars. They are the places where the universe doesn't just obey physics, it experiments with it, where creation becomes curiosity, and curiosity becomes light. To grasp what a magnetar truly is, it helps to shrink the cosmos down to something we can feel, because numbers are so far beyond experience that they lose meaning. So let's bring it home to the gentle magnetic cocoon that surrounds us every day. Here on Earth, the magnetic field is about 50 microteslas. That's 0.00005 teslas. It's just strong enough to guide a compass needle, shield us from solar wind, and paint auroras across the poles. It shapes the migration of birds and the glow of the northern lights, yet it's so weak that you don't feel it at all. A common refrigerator magnet is a few tenths of a Tesla, roughly 1,000,000 times stronger than Earth's field, but still harmless. If you stick it to your fridge, nothing strange happens. It doesn't stretch your atoms or bend the light around it. Now imagine increasing that strength step by step until physics begins to complain. A medical MRI machine, powerful by human standards, operates around 3 teslas. At 10 teslas, you could feel the pull on small metallic objects. At 100 teslas, laboratory magnets begin to rip themselves apart. At 1,000 teslas, chemistry itself would fail. Atoms would be distorted, electrons forced into thin spirals. A magnetar's field is roughly 10 to the 11th power teslas. That's 100 billion times stronger than the most powerful magnet we've ever built on Earth. To put it in human terms, if you stood 100,000 kilometers, about 62,000 miles, away from a magnetar, roughly a quarter of the distance to the moon, its magnetic field could still erase every credit card, stripe, hard drive, and magnetic storage device on Earth. At 10,000 kilometers, your body's atomic structure would start to distort. At 1,000 kilometers, the magnetic gradient would be so intense that it would stretch the very electrons in your atoms into long threads. At 100 kilometers, your molecular bonds would break. And if a magnetar were somehow parked at the distance of the moon, 384,000 kilometers away, its field would be strong enough to rearrange the electrons in your blood, pulling you apart from the inside. We're used to thinking of black holes as the ultimate danger, objects that swallow everything nearby. But a magnetar doesn't need gravity to destroy you. It could tear you apart with magnetism alone. It's one of those staggering cosmic truths that makes you pause. The same quiet force that lets a compass point north, that helps pigeons find their way home, can also become powerful enough to unmake matter itself. Magnetism has always lived in the background of existence. It's everywhere, invisible yet fundamental. Galaxies spin along magnetic threads that guide their gas and dust. Stars form where those threads tangle and collapse. Planets carry magnetic fields that protect their atmospheres and oceans. Even the cells in your brain, tiny electrical impulses firing in rhythm, generate minute magnetic signals. In a very real sense, you and a magnetar are made of the same ingredients, electric charges and magnetic fields woven together at different scales. The difference is one of degree, not kind. If you compared the magnetic energy density near a magnetar's surface to that of Earth, you'd find a difference of roughly 24 orders of magnitude. That's a 1 followed by 24 zeros. But the principles are the same. Magnetic fields arise from moving charges, from spinning electrons, from the rotation of conducting fluids, whether it's molten iron in Earth's core or superfluid neutrons inside a collapsed star. Earth's field is sustained by its geodynamo, molten iron circulating in the outer core, moving under the influence of the planet's rotation. A magnetar's field is born the same way, through a dynamo process, but with speeds and pressures so enormous that it generates a field 100 trillion times stronger. It's a reminder that magnetism isn't just a quirk of physics, it's a universal behavior, emerging whenever energy and motion combine. To visualize the scale, imagine holding a fridge magnet. Its field is strong enough to lift a paperclip against gravity. If that magnet had the strength of a magnetar, it wouldn't just lift the paperclip, it would lift the entire Earth, tear it apart, and scatter its atoms into space. If you placed a coin near it, the coin wouldn't fall or melt. It would disintegrate into plasma. It's absurd, yes, but also a glimpse into how scale changes everything. Magnetars don't break the rules of physics, they simply push them into unfamiliar territory. This is what makes them so beautiful. They remind us that nature operates on a spectrum so wide that our imagination can't easily stretch to cover it. On one end, there's the gentle pull of a compass. On the other, a star's magnetic heart, strong enough to warp the vacuum. And between them, us, living quietly in the middle, under the protection of a fragile magnetic bubble that lets life exist at all. Magnetism has shaped our world in ways we rarely think about. Without Earth's magnetic field, the solar wind, a stream of charged particles from the sun, would strip away our atmosphere, just as it did to Mars. No air, no oceans, no protection from cosmic radiation. Magnetism is the unseen guardian of life. It's the reason we can have compasses, auroras, satellites, and breath. It's also one of the threads that tie us back to the stars. Because in a way, every magnetic field, from a lab coil to a galaxy, is part of one grand continuum. The same laws that describe the magnet in your pocket also describe the invisible magnetic scaffolding of the universe. Our galaxy itself, the Milky Way, is threaded with magnetic lines stretching for tens of thousands of light years. They guide cosmic rays, influence star formation, and shape the flow of interstellar gas. When we study magnetars, we're not studying exceptions. We're studying the most intense expression of a force that touches everything. And so, when you think of a magnetar, don't just imagine destruction, imagine connection. It's the same invisible force that turns your compass needle, scaled up to stellar proportions. It's the same physics that protects our planet, written in a far louder script. The difference is only in magnitude. One field is gentle enough to cradle life, the other fierce enough to unmake it. But they're both manifestations of the same cosmic language. Magnetism binds the universe together. It sculpts galaxies, drives stars, and guards worlds. It threads through atoms, neurons, and living cells. And in the distant sky, in those few small, violent stars we call magnetars, it shows us just how far it can go. In their silence and fury, magnetars are not just extremes. They are reflections. They remind us that the same forces that hold us together can also tear us apart, that creation and destruction are two sides of the same magnetic field. And somewhere between those poles, between Earth's soft auroras and a magnetar's blazing storm, is everything we know. Every life, no matter how brilliant, has an ending. Even the most magnetic stars in the universe, those roaring, impossible engines of energy, eventually grow quiet. For a magnetar, the arc from birth to death is brief but spectacular, a flash of existence that burns with intensity, then slowly fades into silence. A magnetar's story begins in the ashes of a supernova. A massive star, perhaps 20 or 30 times the mass of the Sun, exhausts its nuclear fuel. Its core collapses, forming a neutron star no wider than a city, but heavier than the Sun. If the rotation is fast enough and the convection turbulent enough, the collapsing core acts as a dynamo, amplifying its magnetic field to the extremes we know. 10 to the power of 10 to 10 to the power of 11 Teslas, far beyond anything else in the universe. That moment of creation is violent, hot, and brief. In seconds, the magnetar's fate is sealed. After the explosion fades and the remnant cools, the magnetar enters the phase we see today, a small spinning star surrounded by a fading halo of supernova debris. It's intensely bright in X-rays, its surface temperature around 10 million degrees Celsius. For the next 10,000 years or so, it lives in a state of restless equilibrium, its magnetic field decaying, its crust shifting, its energy slowly bleeding into space through radiation and magnetic storms. But compared to the billion-year lives of normal stars, a magnetar's existence is fleeting, a cosmic adolescence of fury before the long quiet that follows. Over time, the magnetic field that gives the magnetar its personality begins to fade. This magnetic decay happens through a combination of processes: the slow motion of charged particles in the crust, the diffusion of magnetic flux through the superfluid interior, and the rearrangement of the field as it tries to reach a lower energy configuration. Each of these steps releases heat, a process called ohmic dissipation, keeping the surface warm long after the supernova's heat has gone. That's why magnetars glow in X-rays even thousands of years after their birth. Their heat doesn't come from fusion or accretion, but from the magnetic field itself dying. It's like watching a log glow in the dark after the fire is out, warmth radiating from what was once a flame. As the field decays, the magnetar's activity quiets. Starquakes become rarer, flares fade, the X-rays grow softer, the surface cooler. Eventually, the field weakens to around 10 to the 8th power Teslas, still enormous, but no longer enough to power violent bursts. At that point, the magnetar transitions into a more ordinary neutron star, a dense, cooling ember drifting through the galaxy. Its life as a magnetar is over. Many known magnetars still sit at the centers of their supernova remnants, vast clouds of gas ejected during their birth explosions. These nebulae, glowing in radio and X-rays, act as cosmic fingerprints, telling us how recently the magnetar was born. For instance, 1 E2259 plus 586 lies in the middle of the supernova remnant CTB 109, its magnetized core still feeding energy into the surrounding gas. Others, like CXOUJ 164710.2-455216, illuminate the interiors of star clusters such as Westerlund 1, connecting the remnants of death to the nurseries of new stars. In some cases, the fading magnetar may create a pulsar wind nebula, a bubble of relativistic particles driven by the star's rotational energy. This wind inflates the surrounding medium, shining faintly in radio and X-rays, a ghostly echo of the magnetar's early ferocity. But these nebulae too fade as the star slows. Within tens of thousands of years, the once active region becomes cold and dark, blending into the background of interstellar space. One question lingers in every discussion of magnetars: can they collapse further into black holes? The answer depends on mass. A neutron star remains stable only if its mass stays below the Tolman-Oppenheimer-Volkoff limit, roughly 2.2 solar masses, depending on the equation of state of dense matter. Above that, gravity overcomes all other forces, crushing the star into a singularity. Most known magnetars have masses well below this limit, suggesting they'll remain neutron stars indefinitely. However, theory allows for an intriguing possibility. A particularly massive magnetar, formed in an exceptionally large supernova, might briefly exist as a hypermassive neutron star, supported temporarily by rapid rotation and magnetic pressure. As it loses angular momentum and its magnetic field decays, it could cross the stability threshold and collapse into a black hole. If that happens, the collapse might release one last blinding flash of energy, a final outburst before the light is gone forever. This scenario may help explain some of the most powerful gamma-ray bursts ever recorded, which last only a few seconds but outshine entire galaxies. They could be the death cries of collapsing magnetars, disappearing into darkness with one last scream of light. Whether they end in silence or in one last explosion, magnetars are short-lived wonders. 10,000 years of activity is barely an instant on the cosmic clock. The light from a distant magnetar might reach as long after the star itself has already faded. By the time we detect its flares, it could be a quiet ember, adrift in the galaxy. And yet those brief lives leave lasting traces. Their magnetic energy helps shape the interstellar medium, stirring nearby gas clouds and possibly influencing the birth of new stars. Their supernova remnants enrich space with heavy elements: iron, nickel, gold, seeding future worlds. Their flares send cosmic rays and X-rays through the galaxy, rippling through space like aftershocks from creation. Even in death, a magnetar's influence lingers. Its field decays, its light dims, but its fingerprints remain etched into the cosmos. If you could chart the life of a magnetar as a heartbeat, it would look like a sudden spike on a long flat line, a burst of creation, a few thousand years of chaos, and then calm. Yet within that narrow window, it experiences extremes of physics that defy human intuition. In its short life, a magnetar tests every boundary: density, pressure, magnetism, energy, and time. Its lifespan, measured in millennia, is shorter than the span of recorded human history, and yet its story stretches across the universe, a brief magnetic firework in an otherwise patient cosmos. And maybe that's why we find them so compelling, because in a universe that mostly moves in slow glacial time, magnetars are the exceptions, sudden, furious acts of cosmic expression. They live fast, burn bright, and fade in silence, leaving behind only echoes. But in those echoes, we hear something familiar, a reminder that even the most fleeting lives can leave a mark that lasts forever. From far away, a magnetar looks serene, a faint, steady point of X-ray light turning slowly in the dark, calm, patient, almost meditative. Yet behind that calm lies a power so vast that it bends the laws of physics to their limits. It is a paradox made of magnetism and silence, a storm contained within stillness. There's something deeply human in that image, the idea of immense energy hidden beneath restraint. A magnetar doesn't shine by choice. It holds itself together against pressures that should not be survivable. Its magnetic field, twisting space, warping light, and testing the endurance of matter itself. And yet, it endures. It doesn't collapse into a black hole, nor does it explode apart. It simply spins quietly, as though aware that any sudden movement could tear the fabric of its own being. When we study these stars, we're not just learning about astrophysics, we're watching the universe perform its own experiments. Every magnetar is a test case for our deepest theories. It challenges general relativity because its gravity is so intense that even space-time must bend to its magnetism. It challenges nuclear physics because its core is a giant atomic nucleus under pressures no particle accelerator could reproduce. And it challenges quantum field theory, because in its magnetic storms, even the vacuum itself becomes active, polarizing, splitting light, rewriting the properties of nothingness. They are the crossroads where our equations meet their breaking point, where nature itself becomes the laboratory. But beyond the science, there's something poetic about how these objects exist in the universe. Because when you look up at the night sky, what you see feels tranquil. A dome of stillness, stars twinkling in quiet eternity. Yet hidden among those points of light are the loudest things that have ever happened. Explosions brighter than galaxies. Magnetic fields that could tear atoms apart from halfway across a planetary system. Flashes of radiation that cross the cosmos and still have enough power to touch our atmosphere. The calmest view in the world hides the wildest truth. And maybe that's why magnetars feel so strangely comforting. They remind us that peace and power aren't opposites, they can coexist, that the most stable things are often those forged in violence, that even in the quietest corners of space, energy still hums, waiting, patient as time itself. So as the crackling of the fire begins to fill the silence, imagine that calm extending outward, from your room to your planet, to the galaxy, and then to those tiny, fierce stars turning far away in the dark. Each one a whisper of energy, a lesson in balance, a heartbeat in the void. And as their light fades into the background of the night, let it remind you of one simple truth. The universe's most intense things are also its most calm. Good night.